So hi everyone, I am Anuj Kumar working as a Prime Minister Research Fellow, IIT Roorkee. So this is the assignment 5 of Colloids and Surfaces course. So in this particular assignment, we will discuss some questions about the Helmholtz model of electrical double layer and some question related to the generation of surface charge on colloidal particles. Okay, so this is the problem one, in which the given statement is the ionization of surface groups is one of the mechanism by which surface acquires electrical charge. Consider a polystyrene particle. So you have a polystyrene particle, and it is functionalized by the carboxylic group. Okay, and when such particles are brought in contact with water, okay, so the particles are dispersed in water, okay, and the conditions are appropriate for the dissociation of carboxylic. Okay, so the conditions may be you can focus on the pH, or you can exactly the on focus on the pKa value at which the carboxylic group dissociates. So the first question is the what is the surface charge that the particle acquires. So if I simply, if I immerse the polystyrene particles containing these functional groups, it will dissociate COO negative plus H positive groups. Okay, so the surface charge will be the negative one. Okay, so this will be the right answer for this. Okay, normal basic question. Second, you have to identify the charged group on the particle surface. So I have already indicated that COO negative moiety will be the charge group on the particle surface. So this will be the right answer for this. And the third is the identify the counter ions. Counter ions are basically which have a opposite charge to the charge of the colloidal particles. Like say, if you have a negative charge particles, and their counter ion will be the positive charge. Okay, so again I am going to the same slides. So here the H positive are the counter ions in the solution. So this will be the right answer for this. So this is basically a problem dealing with the uh, generation of surface charge, how functional group dissociates, and how it is showing the surface charge on the colloidal particles. Okay, and the second problem is the about some surfactant. So the adsorption surfactant is yet another mechanism by which surface acquires electrical charge. So there may be several mechanisms I have already discussed. Okay, it can be the dissociation of functional groups. Okay, if you have added the polymer having some charge. Okay, third, you are adding the surfactant, and many other mechanism can be there. Okay, so fourth can be the functional groups having the negative or positive charge of the polymer. Okay, so consider a dispersion containing neutral particle to which a surfactant, which is general formula that is given here, RnS3Cl. Okay, R can be any long chain of carbon, or can any group. Okay, so here R is also given. R represents a linear chain of hydrocarbons. Okay, so assume that there is adsorption of surfactant molecules on the neutral particles when they come in contact. Okay, what is the statement is saying? If this is the particle, and if I have added this surfactant, okay, so this R moiety, if this is a neutral molecule, so this R moiety will be the non-polar. So this will add on, and this end will set up on this particle surface, and remaining the NH3Cl outside the surface. Okay, so what is the surface charge that the particle acquires? So after adding how it will dissociate, let me show. So R and S3Cl, Cl is a better living group, it readily dissociates. So R and S3 positive plus Cl negative. Okay, so this will be the surface charge, that is positive, and uh, The next question is you have to identify the charge group. So RNS3 positive will be the sorry. So RNS3 positive will be the charge group on the particle surface, and counter ion will be the Cl negative. Okay. So these are the question, and you have to identify the counter ions and how the charge will generate on the colloidal particle surface. Similar question, let it just like I have discussed the problem one. Okay. So the third problem is some numerical based problem. You have a surfactant-free sulfate latex particles are purchased from a supplier to study electrostatic interactions. So the problem is based on the electrostatic interactions, and the following are the data that is supplied by the supplier. You have a value of mean diameter, and you have the concentration, and you have a specific surface area, or you have density of polystyrene. Okay. So given that the number of sulfate groups, you are given the number of sulfate groups, that is 1.3 10 raised to 7. Let me write it on the next slide because I will solve it here. So number of functional groups will be the 1.3 into 10 raised to 7. Okay. And the electrical charge on an electron is, you know already, the Q value 1.6 into 10 raised to minus 19. Okay. Hmm. Coulomb. And okay, so the you have to calculate first the surface charge density. Surface charge density, surface charge density will be equal to the total surface charge, okay, and divided by the area. Okay. So total surface charge will be number of functional groups multiplied by the charge. And here the diameter is also given. So the diameter is 1.3 micron, sorry, 3.1 micron. So 3.1 micron, or let me convert it to meter, so it will be look like this. So I can write here pi d naught square in the case of the spherical particles are there. Okay. So it is 4 pi r square and 4 pi d by 2 square, 4 by cancel out, just write like this, 1.3 into 1.6, okay, 10 raised to minus 12, and the 3.14, and the d naught value you are getting 3.1 10 raised to minus 6 whole square. Okay. Let me solve it. 1.3, 1.6, and divided by 3.14. Okay. It will be 0.662 and divide by 3.1, that is 9.61. Okay. So this 10 raised to minus 12 and this 10 raised to minus 12 will be cancel out. Okay. And 0.662 divided by 9.61, that will be your 0.068 coulomb per meter square. So you have to convert it to micro coulomb per centimeter square. Okay, so 0.068 and 10 raised to 6 micro coulomb and 10 to power 4 centimeter square. So you basically you will get 6.8 around micro coulomb per centimeter square. You can check the calculation. Okay, yes. And the second is the area per sulfate group in angstrom square. Okay, let me erase it. Okay. So the area per sulfate group, that is the area divided by number of sulfate groups. Okay. So the area will be 5, this one, and the number of sulfate groups is 1.3 10 is to 7. Yes. So you simply calculate it, 3.110 is to minus 6, that will be the meter, and 10 raised to uh, 10, that will be the angstrom square. Okay, and the 1.310 power 7, that will be 3.14 into 3.110 raised to 4 square, and divide by 1.3 into 10 raised to power 7. Okay, so 3.14 is 9.61 10 raised to power 8, 1.3 10 raised to 7. Okay, sorry, 3.14, 9.61 divided by 1.3, that is 23.21, and it will be 10, so that will be 232.1 angstrom square will be the answer for this. So let me put the answers. That will be micro coulomb, and this will be 232.1 angstrom square. So you have to just you need just this value from this data. Okay, in the case of this particle group. Okay, I think this is clear. Okay, uh, let me go to the next problem. Yes. So consider a surface with a surface charge density of this coulomb per meter square. This is the surface charge density, uh, uh, sigma star 6.9 10 raised to minus 2 coulomb per meter square. So the surface is immersed and in water at 25 degree. Assume the relative permittivity of water, that is ER, epsilon R is equal to 18, and the space is given here, the 8.85 and is to minus 2 coulomb per joule. So you have to use the capacitor arrangement to model the electron. Basically, this is the Helmholtz model. Okay, so you have to calculate the strength of the electric field. So use the simple formula you have read in your theoretical classes. Okay. Hmm. Yes, let me put these values here. That is 6.9 10 raised to minus 2. Okay, and divide by 80, multiply by 8.85 10 raised to minus 12. Okay, let me check the units. That is a coulomb per meter square, and here uh, joule per coulomb square. Okay. Hmm. So this term will cancel out, and you will get, let me this here. So, your unit of the answer should be the volt per meter. So you are getting here the joule per meter square coulomb. Okay. Uh, if you know the simple formula, that is V is equal to W on Q. Okay. So the joule per coulomb. Okay. So I can expand it. Joule is equal to volt to coulomb, that is meter square in coulomb. Okay, so you will get the same units. Okay, and this will be cancel out. Coulomb per meter square. Okay, and the 8.85 10 is to minus 12 coulomb square per joule. Okay. Uh, hmm. So let me calculate this. I think it should be the volt per meter square. I'll check it. 6.9 divided by 80 and divide by 8.85. That is, you are getting 0.0097 and 10 raised to 10 or 9.7, that is 10 raised to 7. Okay. So yeah, let me check it again. And 8 to 10 is to minus 12. 6.9 to 10 is to minus 2. Okay, this is the Coulomb square per joule meter. Okay, sorry for that. And it will be the meter. So this term will be the cancel out. So you will get the answer in volt per meter. Okay, and the answer will be you can select between the given options. Okay, yeah, you can check the calculations, but the method of solving is the same. Okay, you have to put these values only in the formula. There is no need to change the units here, and you will get the direct answer in the terms of volt per meter. Okay. The next question is you have to calculate the gradient of the surface potential if the thickness of the double layer is 4.4 nanometer. So you are given this term, that is 4.4 nanometer. In the theoretical classes, you about this, okay, or the gradient of the surface potential or the thickness. So the value of strength of electrical field you will get the from the first question. Okay. For example, I am just putting this value. Okay, 9.5 if I'm selecting 9.5 10 is to power 7. I'm selecting, and the value may be different. You can calculate and okay. So uh, you have to calculate the this value, gradient of surface potential. So it will be E and delta. So 9.5 10 is to power 7, and this will be volt per meter, and 4.4 10 is to minus 9. This will be the meter. Okay. So you will get the answer in volt. Okay. 9.5 multiplied by 4.4, it will be 41.8 and 10 raised to minus 2. Okay, this will be volt, and 41.8, that is minus 2, and converting into millivolt, that is this one. Okay, you will get 41.8 into 10. Okay, uh, 400 this question. Okay, I am solving for this particular value. You can get this value also. You just confirm the calculations, and after that put this value in the in place of strength of electrical field. Okay, and you will get the answer in millivolt. Okay, I think this is clear. Let me check the calculations again. I want to know the exact answer. Yes, the answer is right. Okay, so on the basis of this value, you can calculate uh, the, this gradient of surface potential. 5 10 raised to 7 raised to minus 9 nanometer. So this is the calculation is right. Okay, so this is the last problem of this session. Okay, so here are the this figure one is given here, which is showing the depletion potential as a function of separation distance. Okay, that is practically estimated by the model Asakura Osawa model. Okay, and you have a system of a pair of AABBC particles. So some particles like AA and BB and the CC particles immersed in a fluid containing non-adsorbing polymer. So basically, this is a case of depletion potential measurement. Okay, the corresponding depletion potential is represented by the plots labeled A, B, and C. So this will be for AA and BB and C. So the corresponding depletion potential is represented by the plots this and you have to okay. So the depletion volume is denoted by the B depletion. Which of the following statements are true? You have to calculate or you have to compare the values of depletion potential for these three different particles. Okay. So for the depletion potential, sorry, depletion volume. If you know the formula, that is minus n kbt, or in the force, that is kbt. Sorry, this is p over v over. Okay, so the potential will be greater where the depletion potential, sorry, depletion volume will be more. Okay, so if I consider three cases, just like if I am considering it the plate model, and I'm considering it the plate spherical model, and I'm considering it the spherical. Okay, for let's say for example, so if you know the shape of the particles, uh, okay, so the depletion potential, okay, so depletion potential, am I just I'm just trying drawing this, the depletion potential, okay, and the last one is the this. So you can see here the depletion volume will be higher for the case, the plate like model. Okay, and uh, in this particular case, that is for plate and sphere model, that will be the value of depletion volume for this particular case will be in between these two values of depletion potential. So in this case you have minimum depletion potential. Okay, so the another way of approximating the value of depletion potential, you can see these values here. Okay, so in the case, let me denote the depletion potential by Vt in case of A and the B and the C. Okay, so on the basis of this graph, you can write the depletion potential value will be greater, sorry, in the case of A particles, then B particles, followed by the C type particles. Okay, and the depletion potential is directly proportional to the depletion volume. So the the depletion volume arrangement will be similar to this depletion potential. Okay, so let me choose the correct option, this one. So this will be the right answer. Okay, so this is a tricky question. You have to just focus on the values of the potential values, and you can just approximate the depletion volume according to the values of depletion potential. Okay, I think as I remember, you have read this graph for the case of these three models. First is the sphere depletion potential, depletion volume between sphere and sphere, and the plate and sphere, and the third is the plate and plate. Okay, and this here is the depletion potential is zero in the case where no polymer. Let me show you. So here the suppression distance. Okay, suppression distance is so less, there is no okay polymer in between, so you will get the depletion potential will be G, or at this value, the 2 RG value, that is the sigma value. Okay, I think all the problems are clear to you. Okay, so these two questions were related to the generation of charge on the colloidal particle surface, and the rest three problems, two problems are related to the electrical double layer problem, and the third one is related to the calculation of depletion potential or depletion volume. Okay, so I will finish this session here. So thank you very much for attending the sessions. Okay, let me just close the session.